in considering stochastic differential equations in the last video, we saw um, regular Brownian motion and, of course, geometric Brownian motion. And in this video, we'll be looking a bit more intently at the idea of geometric Brownian motion. Okay, now we saw that for regular Brownian motion, right? For an expression like the s of t, of course, we could also see the x of t, which we used in the other video. So the s of t equals mu s of t dt plus sigma s of t dwt. So the s of t here makes it geometric. So if you remove s of t from each of this, it becomes the regular Brownian motion. So geometric Brownian motion, GBM, is a stochastic process widely used to model stock prices and other financial quantities. It is defined by the stochastic differential equation, the s of t equals mu s of t dt plus sigma s sub t dwt, where s sub t is the value at time t, mu is the drift, or if you like, you can call that the growth rate, sigma is the volatility, and then w sub t is the standard Brownian motion. So this second part is what makes it actually a random, a stochastic process, because you see volatility, you see randomness. Brownian motion talks about randomness. So the key intuition here is that geometric Brownian motion represents exponential growth with randomness. So we have a deterministic part rather, mu s sub t dt, and a random part, sigma s sub t dw sub t. So, and we have important properties like s sub t greater than 0, then log returns are normally distributed, and prices follow a log normal distribution. So the explicit solution of a geometric Brownian motion, which we already saw in the last video, is that the solution to the stochastic differential equation, which we saw up there, is actually s sub t equals s naught exponent u minus half sigma squared multiplied by t plus sigma times w sub t. Now, the reason for that is most likely because, from this expression, we can factorize st, and then we can do separation of variables, and from there we can then deal with the other parts of the problem. That's where the exponent should be coming from. And then we have the idea of log transformation. So if we take logarithms of both sides, we have uh, natural logarithm of s of t being equal to natural logarithm of s naught. And of course, if we take natural logarithm of exponent, the exponent disappears. So we then have mu minus half sigma squared plus t, multiplied by t rather, uh, plus sigma omega sub t. This shows that the log of s of t is normally distributed with mean ln s naught plus mu minus half sigma squared multiplied by t, and variance sigma squared multiplied by t. Like that. That's what the log transformation shows us. Then talking about the moments of GBM, the expected value, which being the first moment, is the expected value of S sub t, which is S naught e raised to power minus mu t. E raised to power mu t, sorry. And then the variance is the variance of S sub t, which is S naught squared e raised to power 2 mu t. So it's more like squaring this, and then we have e raised to power sigma squared t minus 1, like that. Of course, I can already imagine to show this, it's going to be a kind of lengthy process. If you need me to show that for any whatever reason, you can let me know so I can take the pain. Then we have the discrete time approximation. So for simulations, we use s sub t plus delta t equals st exponent mu minus half sigma squared multiplied by change in t plus sigma square root of uh, change in t times z, where z is normally distributed with mean 0 and normal and variance 1. Okay, so and then of course that can be shown via simulation here, where we have the single gradient, I don't know why I'm calling that G gradient, geometric Brownian motion, having set all the necessary parameters. So this is all simulating a single GBM path. So you have parameters S naught, that's 100. If you take S naught to be 100 and we take mu to be 0.05, that's the growth rate. Sigma, that's the volatility of 0.2. We take time to be 1.0. N is 252. Then the T is T over N. Then we can have random shocks. We have Z to be random between 0 and 1. And then we initialize. S is NP zeros, that's in 100 places because oh, that's 252, right? Then we initialize, we simulate now. So this is us writing out the formula as S naught exponent of the whole expression we have up there. a square root of dt, as you can see. So we can then generate this single GBM path. So we can also go for multiple GBM paths, right? For instance, what you have here is for 50, but you can also see how it grows, right? So for multiple geometric Brownian motion paths, right? So you can set the number of paths, and then the path will now be, so you set zeros n comma m, therefore I in the range up to whatever m you set, right? Then you have your z random normal, then you set the path to the initial value s naught, which will, of course, this code works with the s naught we've defined up here, which is s0 here. Okay, and then we fix the formula mu 0.5 sigma squared delta t blah blah. So now this is for 50, like I said. Imagine you can also do one for this. So if you have this, you just run it, you get this one. Okay, we can go to two. So if you need two parts, so you can do that. So this is two right there. Of course, if you run it differently, to keep running it, it keeps shifting shape. Then you also have three. Okay, for three, you have this. So of course, the three can also behave differently as you keep changing it. So you can go to four now, change it to four. So four paths. You can have four paths like this. Then you can have five paths. Okay. And from there, let's jump to 10. Okay. You have 10 paths. So you keep running, it keeps changing. As for 10 paths, so let's jump to 20, 20, 20. Then we have 30. And then 40. And then 50. So you can keep going like that. Let me stop at 100. Yeah. All right. So it goes like that. So then we have another example here. So if S naught is 100, that's the initial stock price. If you're looking at a stock, the mu, the growth rate is 0.1, the volatility is 0.3, and time is 1. Let's say maybe 1 week, 1 month, 1 year, whatever the time unit is. Then the expected value, of course, will be expected value of ST, which is 100 e raised by 0.1. Of course, that follows the idea of expected value we had seen before. This is S naught e raised by mu t. And then, of course, for variance too, you also have this. So just fix up all the values, and then we can simulate that using a code. So S naught is 100, mu is 0.1, sigma is 0.3, time is 1, expected value, you write it out. I mean, you define it S naught times NP. That's from NumPy now you can get exponent, mu t. Then for variance, same thing. So if you simulate, you get 110.5 for expected value, 1150.24 for variance, like this. Okay, then you can also have a Monte Carlo verification. So we simulate many paths and compare empirical mean with theoretical value. So this is the theoretical value, S not raised by mu t. So if you want to use Monte Carlo verification now, so you imagine doing like 10,000 paths and comparing with the theoretical value, which we have up there. So going by Monte Carlo, we expect that the values are close by. So this is taking a lot of time because we have 10,000 steps. So you see, we have 110.6, 110.5. That's pretty close. So if you keep running it, to keep, I guess it to keep changing, but the values will be very close. Okay, 110.76, 110.552 or so. So things like that. So in summary, we say that geometric Brownian motion model stochastic exponential growth. So the process satisfies d s sub t equals mu s sub t dt plus sigma s sub t dwt, and then the solution is st equals s naught exponent mu minus half sigma squared t sigma W sub t. So log prices are normally distributed and widely used in finance and option pricing. So that's some financial maths, right? When you hear option pricing, we are talking financial mathematics. Okay, so we have some practice problems now. So the instruction, solve the following problems unless stated otherwise. Assume that the geometric Brownian motion is given as the s of t mu s sub t dt plus sigma s sub t dw sub t, like this. So you have question. So I'll just flash the question, then I'll name the ones I'm going to solve. Okay, basically I'm solving question 15 only. So you have question 1 to 3 here. I have question 4 to 6 here. This is 4 to 6 right here. And then you have 7 to 10. 7 to 10 here. And then 11 to 14. So you have 11 to 14. Then you have to 15 to 18. And then finally, you have 19 to 20, like this. So yeah, but I'm solving 15, like I said, because it looks a bit complicated. So I'm going for that. 15 is what I'm dealing with. So want to show that. So to show that the expected value of s sub t raised power n is equal to s naught n e raised power n mu t plus half n into n minus 1 sigma squared t. So step one, we have, we start from the GBM solution. So we start from the GBM solution, and that is st equals s naught exponent mu minus half sigma squared t plus sigma omega, w sub t. I am always tempted to call that in omega. That's step one. So in step two, we raise to the power of n, raise to power n. Why are we raising to power n? This is already st, right? But what we are looking for is expected value of st raised to power n. So we have to raise that to power n. So if we raise to power n, it means we have s sub t power n equals s naught power n, then exponent. So when we raise exponent to power, so it means the power just multiplies the exponent, right? So exponent n comes in here now, mu minus half sigma squared multiplied by t. Then the n also affects this, w n sigma w sub t. Now, what we are basically saying is that if you have, say, say you have st to be s naught e raised power 3t, right? 3t, let's say 3t plus 4, okay? So that means that st raised power n will be s naught e raised power 3t plus 4 raised power n. So you know that power, because n is power now, it is going to multiply what you have up there. So it's going to be s naught raised power n e raised power 3t plus 4 multiplied by n, so that you can then have s naught raised power n, that's s naught raised power n, e raised power 3tn plus 4n, like that. So that's what is happening there. But because we didn't write it, because this is heavy to write at the top, so exponent, just know n is going to affect this like that when we raise it to power n. So with that taken, uh, with that done, then we can go for step 3. Step 3 now, we can take expectation. Take expectation. So when you take the expectation, what do you have? You have exponent, expectation of STN. Yeah. Expectation like that equals S naught. S naught raised power n is a constant. So it will always remain. So then we have expectation of exponent of n into mu n into mu minus 1 over 2 sigma squared multiplied by t plus n sigma w sub t, like this. Okay, so we factor out deterministic part. So factor out deterministic part, deterministic part. So if you factor that out, that means that the expected value of st raised to power n is equal to s naught raised to power n. So for the deterministic part, then we have, okay, now this is exponent. It has nothing to do with t, right? Okay, yeah. The expected value is only going to affect the winner process. So anything that doesn't involve winner process, like this part now, we can factor it out. So S naught exponent into n mu minus half sigma squared t. Okay, because expectation is only going to affect the winner process. So plus the expected value now, the expected value of the exponent. So the exponent affects if this and this together. Hope I wrote that well from the one. Yeah, it affects all of that. So that'll be expected value of the exponent of n sigma w sub t, like this. So with that in place, then we continue to tidy things up. So we go to step 4 now. So we have step 4. So step 4, we use moment generating function of normal distribution. Moment generating function of normal distribution to continue the process. So since we know that the winner process follows normal distribution with mean zero and variance time, so then we use the fact that the expected value of e raised power a w sub t is the same thing as e raised power half a squared t, like that. So if we use that, right, then if we let a be n sigma, right, that means that the expected value of e raised power n, so this a now, so that's n sigma w sub t is simply going to be e raised power half n squared sigma squared t, because a now is n sigma, so n squared sigma squared t. So, and with all of that in place now, we can go for the next step, which is to combine terms. So we combine terms. So to combine the terms now, we then have the expected value of st power n, st power n equals s naught power n exponent n into mu minus half sigma squared multiplied by t plus half n squared sigma squared t. So that's us combining because we've taken care of that part. This whole thing now. That was why we followed all this process. And with all of that in place now, we can then simplify exponent. So that's step 5 is to combine terms, right? Step 5, we combine terms. So step 6, we simplify. Step 6, we simplify exponent. Simplify exponent. So to simplify the exponent, that's here we are focusing on this now. So we know that n into mu minus half sigma squared multiplied by t plus half n squared sigma squared t is equal to n mu t minus half n sigma squared t plus half n squared sigma squared t. So that's n mu t plus half n into n minus 1 sigma squared t. So, I mean, this is n mu t, right? Then half n is common here, this half n. So if you take it out, so it means that we have we have half n sigma squared t, half n sigma squared t, but we have n remaining here, then minus. So half n sigma squared t takes care of this. Or if I do that slowly, okay, if I do that slowly, we have so this is what's happening. N mu t, then we have plus half n squared sigma squared t minus half n sigma squared t. So I switched this over, okay, so that we now have n mu t plus half, half n sigma squared t is common to this and this. So, and that means for if we take half is here, one n has gone, so we have one n left here. Sigma squared is out, t is out, minus everything here is out. So we have this. So that's the expression we have. And we try to go finalize the whole thing now. And we go for step 7, which is the final result. So step 7, we have the final result. Final result, that will be expected value of s sub t power n equals s naught raised power n e raised power n mu t plus half n into n minus 1 sigma squared t. And that is what we expected to prove. So we have some key insights here. Key insight that we get from this. First of all, we see that GBM, geometric Brownian motion, is log normal, which we already saw before. It's log normal. That implies that powers of ST remain tractable. So even the powers can still be properly dealt with. All right. Then two, the extra term, the extra term, which is half n into n minus 1 sigma squared t. So this extra term here, okay, comes from variance. So comes from variance of Brownian motion. It comes from variance of Brownian motion. Okay. So that's what we see there. So with this, we come to the end of this interesting video about geometric Brownian motion. It's quite an interesting one. Okay, so don't forget to try your hands on the problems. So once more, I flash them. 1, 2, 3. You have 1, 2, 3 here. All geometric Brownian motion given as ds sub t equals mu s sub t dt plus sigma s sub t dw sub t. So 1, 2, 3 like that. You have 4 to 6. 4 to 6 here. Then you have 7 to maybe 7 to 11. Yeah. And then you have 12 to 15, we have 16 to 20. Try your hands on them and see how well you understand this. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of the channel by clicking on join. That gives you special privileges like being the first to see some videos or seeing some videos exclusively. You can also request for PDF copies of my notes, or we can hang out together to discuss whatever interests you on this channel, either physically if you're in the same geographical location, or online if we are not, I mean, if you prefer that, and or we are not in the same location. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.